This is the 5th video dedicated to Bessey Shuffle diagrams. So as a reminder, a shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also recall that the 8 digits 1 through 8 are color-coded as follows. The digits 1, 4, 6, 7 are color-coded black, and the digits 2, 3, 5, 8 are color-coded red. We do this to help us keep track of the movement of these two sets of position values for the cards. If the cards in positions 1, 4, 6, 7 stay in those positions after performing a shuffle, this means that the cards in positions 2, 3, 5, 8 will stay within those position values. That being the case, we're looking at this situation here. If it happens that the cards originally in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8, and vice versa, then we say an inversion has occurred, and we represent it in this way, using the names of our sets A and A complement. Relating all of this to Bessey sequences expressed using zeros and ones, we find that there are only two possibilities. Either our ones will be in positions 1, 4, 6, 7, with the zeros in positions 2, 3, 5, 8, or in the case of the inversion of this sequence, we get the Bessey sequence in which the zeros are now in positions 1, 4, 6, 7, and the ones are in positions 2, 3, 5, 8, where all of this is summarized here below. Picking up where we left off in the 4th video in this series devoted to Bessey Shuffle diagrams, we're going to look at the 17th shuffle as listed on the top left side of the screen. It's called a 50% coding, and here is the cycle permutation representation of that shuffle. So let's go ahead and illustrate a 50% coding. So as always, we'll begin with the ordered packet 1 through 8 to help us keep track of the movement of the cards. So a 50% coding is where we simply count out half the cards, 1, 2, 3, 4, and drop the rest on top. We call that a 50% coding of the cards. By the way, the word COAT, C-O-A-T, stands for count out and transfer. It's an acronym. So here is the new ordering of the cards. We can now write the Cauchy 2-line notation for our permutation. It will be as follows. The top row consisting of 1 through 8, and our new ordering making up the bottom row. So we see that we have 5, 6, 7, 8, 4, 3, 2, 1. Cauchy's 2-line notation can now be written in 1-line notation, also called cycle notation. Recall how this works is we see that 1 goes to 5, so there's an arrow from 1 to 5. 5 over here goes to 4. 4 goes to 8. And then 8 goes to 1, so it wraps around, completing a 4 cycle, 1, 5, 4, 8. Looking at what happens to the value 2, we see that 2 goes to 6, 6 goes to 3, and 3 goes to 7, and finally 7 goes to 2, so it wraps back around, resulting in a second 4 cycle. This accounts for all 8 digits. If we color code this cycle notation of our permutation, we obtain the following. Black 1 goes to red 5, which goes to black 4, which goes to red 8, which wraps around and goes to black 1. Red 2 goes to black 5, which goes to red 3, which goes to black 7, which wraps around and goes to red 2. So we see here that each value gets sent to a value of the opposite color. When that happens, inversion has occurred. So again, this means that the cards that originally began in positions 1, 4, 6, 7 have now moved to positions 2, 3, 5, 8 in some assignment. In fact, the assignment is given by our cycle description of the permutation. If we now look at the graph, which is found at the top left of your screen, we can see how the Bessey Shuffle diagram was constructed. We know that 1 goes to 5, which goes to 4, which goes to 8, which cycles around to 1. So if we look at 1 goes to 5, so it goes down here. 5 goes to 4, straight across. 4 goes up to 8. 8 goes over to 1, and that completes that cycle. So that's our first 4 cycle. We also say that the values 1, 4, 5, 8 are members of the same orbit. If we take a look at 2, 2 up here goes to 6, which goes to 3, which goes to 7, which wraps around and goes to 2. So if we start at 2, there will be an arrow from 2 to 6, an arrow from 6 to 3, an arrow from 3 to 7, and then an arrow from 7 back to 2. That completes that second 4 cycle. And those 4 values constitute a second orbit. And as indicated up here, inversion has indeed occurred. So what does that mean relative to a Bessey sequence involving the digits 0 and 1? Well, what it means then is if we perform a 50% coding of this packet, the 0s and 1s will switch places. So we'll get the inversion. So why don't we quickly just show that. So 1, 2, 3, 4, that's 50% of the cards. Drop the rest on top. Did we get an inversion of the original sequence? We did indeed. It now begins with 0, then 1, 1, 0, followed by 1, 0, 0, 1. Our next shuffle is a 50% cutting of the cards, and it leads to a very curious shuffle diagram, as you can see, on the right-hand side of the top row. So let's go ahead and demonstrate this. So we begin with our packet of 8 clearly marked cards. So a 50% cut is where you just move the top 4 cards without rearranging their order. You move the top 4 cards to the bottom. That is a 50% cutting of the cards. Well, what's the new ordering of the cards? Well, you can probably anticipate what it is, but let's go ahead and just set it out so we can clearly see. And writing this permutation in Cauchy's 2-line notation would look like this, where the second row consists of 5, 6, 7, 8, 1, 2, 3, 4. Cauchy's 2-line notation can be rewritten or converted to cycle notation as follows. 1 goes to 5, so there's an arrow from 1 to 5. 5 goes to 1, so it wraps around. So we get a 2 cycle, also called a transposition. So 1 and 5 just switch places. What about 2? 2 goes to 6, so we have an arrow from 2 to 6. And then 6 goes back to 2, so we have a second transposition, or 2 cycle. 3 goes to 7, so we have an arrow from 3 to 7, and 7 goes back to 3, so we have a 2 cycle, or transposition. And finally, 4 goes to 8, and 8 goes to 4, so we have a 4th transposition. Color coding the cycle notation of our permutation, we obtain the following. And we can readily see that inversion has occurred. So black 1 goes to red 5, which wraps around to black 1. Red 2 goes to black 6, which goes to red 2. Red 3 goes to black 7, which gets assigned to red 3. Black 4 goes to red 8, which gets assigned to black 4. So we have the following. each value gets sent to a value of the opposite color. And we know when that happens, inversion has occurred. And you can probably, in your mind's eye, picture what's going to happen with our quintessential Bessey sequence 10010110 when we perform a 50% cutting of the cards. Because if we just push off the top 4 cards without rearranging their order relative to each other and just move that little block of 4 cards to the bottom, we will get an inversion of the original Bessey sequence. We will now get the sequence 0110 followed by 1001. And taking a look at the Bessey Shuffle diagram for a 50% cut, we get this rather fun wheel looking diagram where there will be a double arrow between 1 and 5, so 1 and 5, a double arrow between 2 and 6, 2 and 6, and then a double arrow between 3 and 7, and also one between 4 and 8. And then we've indicated here that inversion has indeed occurred. Moving on to our next shuffle, which I have called the Bessey 1-1, and to my knowledge, this shuffle does not actually have a name out there in the larger world of mathematical card effects. So I needed to give it a name so that I could refer to it. So to demonstrate this shuffle, we'll begin with our ordered packet 1 through 8. And how this shuffle works is you hold the cards in what's called biddle grip. This is called biddle grip, B-I-D-D-L-E. And you take the top card off into your other hand, and then you take the bottom card, just one, the bottom card into your other hand, onto the top, onto the one that you've just set there. And then you take top again, and then bottom, top, bottom, top, and then bottom. So you're just taking one from the top and bottom alternately. So what order does that result in? Well, let's set these out and see. Well, if you look at that, it's quite a mess, really. So we get 5, 4, 6, 3, 7, 2, 8, 1. And so if we look at Cauchy's 2-line notation for this permutation, we get the following: 5, 4, 6, 3, 7, 2, 8, 1 on the bottom row of the 2-line notation. And then we can convert this to cycle notation by just following the movement of these values. So for instance, we see that 1 goes to 5, so there's an arrow from 1 to 5. 5 goes to 7, so 5 goes to 7. 7 goes to 8, so we have an arrow from 7 to 8. And then 8 goes back to 1, so it cycles around, so we get a 4 cycle. Next, if we look at what happens to 2, 2 goes to 4, so we have an arrow from 2 to 4. 4 goes to 3, 3 goes to 6, and then 6 goes to 2, which cycles around, so we get a second 4 cycle. If we color code the digits, we get the following. And remember, the color coding for the digits is as follows. 1, 4, 6 are color-coded black. 2, 3, 5, 8 are color-coded red. This will help us keep track of the movement of the objects in those positions. It will also help us readily detect whether inversion has occurred, which it has occurred in this current example. So we see that color coding, we get black 1 goes to red 5, which goes to black 7, which goes to red 8, which wraps around and goes to black 1. Red 2 goes to black 4, which goes to red 3, which goes to black 6, which wraps around and goes to red 2. So we see here that each value gets sent to a value of the opposite color. And when that happens, we know that inversion has occurred. So in particular, this tells us that if we begin with the Bessey sequence 1001, 0110, and perform a Bessey 1-1, we will get an inversion of this sequence. So let's go ahead and just demonstrate that. So the Bessey 1-1, you take the top one, and then the bottom, One from the top, one from the bottom, one from the top, one from the bottom, one from the top, one from the bottom. There's only one left. So let's see if inversion has occurred. It has indeed. The sequence is now 0, 1, 1, 0, 1, 0, 0, 1. So all of the cards that were originally in the positions marked by 1s are now in the positions originally marked by 0s. In other words, the cards originally in positions 1, 4, 6, 7 have now been moved to positions 2, 3, 5, 8 according to the assignments described here in our permutation notation. If we take a look at the graph, the bottom left, we can see that the Bessey 1-1 is quite a chaotic little shuffle, but nonetheless, it does not destroy the fundamental nature of a Bessey sequence. Remember, Bessey sequences of order 8 come as a pair. So a shuffle is a Bessey shuffle if it either preserves the Bessey sequence, you get the exact sequence form back, or it inverts it. So why don't we go ahead and just step through this. So 1 goes to 5, goes to 7, goes to 8. Start at 1, 1 goes to 5 down here, which goes to 7, which goes to 8, which wraps around to 1. So we get this 4 cycle, which again means that the numbers 1, 5, 7, 8 are members of the same orbit. And now if we take a look at 2, 2 goes to 4, which goes to 3, which goes to 6, which goes back to 2. So if we start at 2, it goes down to 4, 4 goes to 3, 3 goes across to 6, and then 6 goes all the way across back to 2, completing that cycle, which gives a second orbit of the same size, namely 4 elements. So there are no fixed points here either. Every object in those 8 positions will be moved to some other location. I have a note down here that the Bessey 1-1 is the inverse of Shuffle 11, which we saw earlier in this series. So let me just quickly remind you of what Shuffle 11 was. It was the mange over under. The overall shape of this diagram is identical to the one for Bessey 1-1. The only difference is the arrows are reversed. All of the arrows here are reversed from what they are in the shuffle diagram for the Bessey 1-1 shuffle. So, of course, this will mean that if you perform a mange over under followed by a Bessey 1-1, it returns the packet to its original order. Or if you perform a Bessey 1-1 first, followed by a mange over under, that will also return the packet to its original order. So why don't we go ahead and just illustrate one of those directions here. So here we have our ordered packet. So let's go ahead and perform the mange over under first, followed by the Bessey 1-1. So recall, the mange over under is where you push over the top card. Now this next top card goes over the one in your other hand, and then the next card goes under. Over, under, over, under, over. Well, if we follow that with the Bessey 1-1, we will reset the packet. So we take the top, one from the top, one from the bottom, top, bottom, top, bottom, top, bottom. There's only one card left. And so if you really think about what those shuffles are doing, in this case it shouldn't be all that surprising that we get back to the original ordering of the cards. Now what may not be clear to most observers is the fact that you can perform the mange shuffle as many times as you like and the Bessey shuffle that same number of times, but mix how you do that. So for example, you could perform the mange over under twice, and then perform the Bessey 1-1 just once, and then perform the mange over under one more time, and then the Bessey 1-1 2 times. You'll reset the packet. The key is you just need to perform the mange over under and the Bessey 1-1 the same number of times altogether. But the exact order in which you do that will not matter. Now that's not as clear to a majority of observers. For our last shuffle today, we're looking at the Bessey 2-2. So let's show you how this shuffle works. And this is a second shuffle for which I'm not aware of a name for it. So I had to give it a name, so I just call it the Bessey 2-2. Now you can probably guess how this one works if you just think about what the Bessey 1-1 involved. So we'll begin with our order packet, as always. So a Bessey 2-2 is where you take the top two cards one at a time. So you go 1, 2 from the top, 1, 2 from the bottom, 1, 2 from the top, 1, 2 from the bottom. So that is the Bessey 2-2, which results in the following new ordering of the cards. And then if we describe this in Cauchy's two-line notation, we obtain the following. We see that the new ordering is 5, 6, 4, 3, 7, 8, 2, 1. And that two-line notation can be converted to cycle notation as follows. 1 goes to 5, so we have an arrow from 1 to 5. 5 goes to 7, we have an arrow from 5 to 7. 7 goes to 2. 2 goes to 6, so we have an arrow from 2 to 6. And then 6 goes to 8. And finally 8 goes to 1, which wraps around, so that completes a 6 cycle in this case. And the remaining two values are accounted for as follows. 3 goes to 4, so we have an arrow from 3 to 4, and then 4 goes back to 3. So that completes a 2 cycle, also called a transposition. If we color code our digits, remember digits 1, 4, 6, 7 are color coded black, and digits 2, 3, 5, 8 are color coded red. And if we do the color coding, we can see that we get an alternation of colors, including, quote, going around corners, cycling back around. So in particular, this means that black 1 goes to red 5, which goes to black 7, which goes to red 2, which goes to black 6, which goes to red 8, which gets sent over to black 1. Red 3 goes to black 4, which gets sent back to red 3. So in particular, what this tells us is each value gets sent to a value of the opposite color. And when that happens, we say that inversion has occurred. And we can quickly demonstrate that using our quintessential Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So let's go ahead and perform the Bessey 2-2. So we do 1, 2 from the top, 1, 2 from the bottom, 1, 2 from the top, 1, 2 from the bottom. Let's see what has happened. Do we get the inversion? We do indeed. Now we get 0, 1, 1, 0, 1, 0, 0, 1. So all of the cards that originally were in positions marked by 1s have now been moved to positions that were originally marked by 0s. So they've switched places. So we call that the inversion. So let's take a quick look at this final shuffle diagram. So it's on the bottom row, but on the right, here it is. So we see that 1 goes to 5, 5 goes up to 7, 7 goes across to 2, 2 goes down here to 6, 6 goes up to 8, and then 8 goes back to 1. So that completes this 6th cycle. And we say that all of the values listed here are members of this same orbit. So they just get moved around among themselves every time this shuffle is performed. And finally, the remaining values that we have not accounted for are 3 and 4. Well, 3 and 4 form a transposition. So down here we'll see there is an arrow from 3 to 4, and there is also an arrow from 4 to 3. So those just go back and forth forever. So the objects in positions 3 and 4 trade places every time this shuffle is performed. And because of the 6th cycle here, we know that the Bessey 2-2 has order 6, meaning you would have to perform this shuffle 6 times to reset the packet of 8 cards back to its original order. And over here we've indicated that inversion has indeed occurred. And we are finally ready to take a look at an application of all of this. So I have here 8 cards, and you can take a look at those, and I don't believe anyone on planet Earth could look at these cards and see any structure to them that will relate to the ending of our routine. No one will be able to anticipate where we're headed with this. I guarantee you. So here they are. So here are 8 cards of various values and colors and suits. So what we're going to do is we're going to go ahead and perform these shuffles that we've just introduced, and we technically can perform any of them in any order and in any quantity. We truly can. So you could do 2 50% coatings, followed by 3 Bessey 2-2s, followed by 1 50% cut, followed by 12 Bessey 1-1s if you wanted. And you will still finish with the ending that we will finish with. Okay, so that's important to know. Okay, so let's go ahead and have you, if you were here, I would just have you randomly choose the order in which we'll do these. But since you're not here, I'll just have to choose. So maybe you'll ask for the Bessey 1-1 first. So let's go ahead and do that. So this is where you take the top, and then the bottom, top, bottom, top, bottom, top, and then the bottom goes on top. So that's the Bessey 1-1. Which one would you like next? Maybe you'll say the 50% cut. So this is where you just push over the top 4 cards and move them to the bottom. That's a 50% cut. Maybe you'll say the Bessey 2-2 next. That's just fine. So we'll go 1, 2 from the top, 1, 2 from the bottom, 1, 2 from the top, 1, 2 from the bottom. And finally, if we're going to do each of these just once, which we don't have to do that, but to keep the video from being too long, so let's do a 50% coating. So 1, 2, 3, 4, that's 50% of the cards, and then you just drop the rest on top. Okay? Now, I really want to emphasize that we could continue. We could not do some of these. We could do more of one than the other, and we can do them in any order. That really, really is true. And try it out for yourself. And maybe as a added bonus, let me just point out something that is very, very powerful regarding a 50% cut. Now, a 50% cut, once again, is where you just push over the top 4 and then move them to the bottom. Well, that's just perhaps a little too simplistic looking, you know, that you're breaking off exactly half and then moving them to the bottom. It just seems like you're being very careful, because otherwise the whole thing's going to fall apart. Well, a better way actually to perform a 50% cut, which I've talked about extensively on the Hidden Structures channel, is something called a Charlier 1. A Charlier 1 shuffle. So let me go ahead and just demonstrate that for you, because if you haven't used it before and would like to use that instead of this kind of obvious pushing over 4 and then moving them to the bottom, this is a much more convincing way to go. So Charlier 1, how does that work? Well, what you do is you push over the top card, and now from the bottom you push over the bottom, just one card, and you put it on top. The top card here on the right goes on the bottom card here on the right goes on top, top to bottom, bottom to top, top to bottom, bottom to top. So that is actually equivalent to just pushing over half the cards and then changing the order of those 2 packets of 4 cards. It really is. It's a 50% cutting of the cards. Okay, well, anyway, the point is, despite all of the mixing that we have done and all of the mixing we could do, let's go ahead and just kind of finish this. And there's a number of ways of finishing. If you've watched any of the videos on the Bessey Sequence playlist, a fun way to finish would be to do this triangle deal. Okay, so you just deal out into a triangle clockwise like this, And then you just stack in the opposite order, so in a counterclockwise order. Okay? So that's one way to undo the structure of a Bessey sequence so that we now have two blocks of related cards. Okay? So what this would mean then is if we just give the spectator the top four cards and we retain the bottom four for ourselves, or you can just actually just create two piles in that fashion. That would be fine too. Maybe that would be better so that you don't associate these cards with them. You're just breaking the cards in half. It will result in these two sets of cards. We get a 7, 10, 2, Jack. Let's see, what do we get down here? We get a 3, 2, 5, Ace. Oh, that's curious. Whoops, I guess I need to move that over a little bit. Well, I don't know if that means anything to anyone, but if you've made note of something that I've had in plain view for this entire video, I have a piece of paper over here that's kind of been almost in the way. I maybe shouldn't have left it there the whole time. So I think I've written some kind of a prediction about what would occur after all of the random choices that you've made that have determined the order of these cards in the end. So let's see, what was the prediction I wrote? The sum of one pile equals the product of the other. What does that mean? Is that actually true? The sum of one pile equals the product of the other. Well, let's see. If we were to multiply these values, what happens? See, 3 times 2 is 6, times 5 is 30. We normally associate ace with 1, so 30 times 1 is 30. What about the sum of these over here? So 7 plus 10, 17, plus 2 is 19, plus 11 is 30. We normally count the Jack as an 11. So those add up to 30. These, when multiplied, give you 30. And that's exactly what I predicted would occur despite the randomization that was performed according to free choices made by you, the spectator. How is that even possible? Okay, so let's take a look at how that's possible. And I might even give you a different way to finish. I'm not sure how happy I am with that particular finish, with dividing the cards in half and that kind of thing. Okay, so how does this work? This set of 4 cards will be important to keep together, and this set of 4 cards will be important to keep together. Okay? It's because the product of these is 30 and the sum of these is 30 as well, and so our prediction will be shown to be true. Okay, well, how did I begin it? Well, what I did was I built a Bessey sequence relative to these two categories. Now, you may want to, let me just kind of show this here because it really may help people to kind of wrap their minds around some of this. I'm just putting out 1. So what I'm trying to show here is imagine the ones are being associated with these cards. Okay, so imagine like writing a 1 on them in addition to their current card values. And then the remaining cards over here would be, quote, zeros. These are zeros and these are 1s. Okay? So to build a Bessey sequence, what do I need to do? Well, if I begin with a leading 1, these are the 1s. I could just take any one of these, like this. So this is like a 1, and now I need a 0, and another 0. So just any two of those, and then a 1. So this is like having 1, 0, 0, 1, and now I need a 0, quote, 0, and then a couple of 1s. These are being associated with 1s, and then I need, quote, a 0, a card associated with a 0. So technically this is now a Bessey sequence relative to those two separate sets of cards. Okay, so that's how I began. I began that way. Now, perhaps an easier way to begin that I'll go ahead and just show you right now is to go back in time. Let's go ahead and just separate these again. And it looks like we have a couple of choices here, don't we? Because we have two twos. Okay, so those when multiplied give you 30, which is what we need. These multiplied, these when added give you 30 as well. Now I may have switched the black 2 for the red 2, but it doesn't actually matter. We're only focused on card values. Okay, so I think it may be easier for most people to go ahead and just create this little packet where the card values when multiplied give you 30. Create a second packet where the card values add up to 30. Okay, so I think that's probably a little easier to kind of start there. And then we're going to go ahead and just put either set of 4 on top of the other. Okay, it doesn't matter. Now what you can do is use Werner Miller's very clever triangle deal to convert this into a Bessey sequence. And it's kind of a classy way to do it. And you've seen it already in this series, in this current series. So this is where you deal into a triangle like this, clockwise, let's say. And then when all of the cards are dealt out, you pick up the first pile again, and then you just stack in opposite order, or in other words, counterclockwise. And as you can check, this will now be a, quote, Bessey sequence relative to those two sets of card values. Well, what it means then is this is now protected against any Bessey shuffle. Now, Bessey shuffles will either preserve this structure type or convert it to its inversion. And it won't matter if it does actually change it to its inversion. Okay, so whether it preserves it exactly as is in terms of its Bessey organization or Bessey structure, or inverts it, it won't undermine anything we will accomplish in just a moment. Okay, but this is now a Bessey sequence. So really what I'm suggesting is you begin with those two piles of cards, one whose values multiply to 30, one whose values add to 30, just stack those, and then just use this very clever triangle deal to do the work of putting it into a Bessey structure, a Bessey sequence. Okay, and then from this point, you can perform any of the shuffles that I've shown you, any of the 20 shuffles I have shown you in this series so far. So if you want to go back in time, you can perform any of those in any quantity, in any order. You can leave some off the list, you could do all of them, and you can do as many of each of them as you like in any order relative to the others. Okay, I mean, that's the amazing thing. This structure is virtually indestructible. In fact, in some ways, it is indestructible if you are applying a Bessey shuffle. And as you're discovering, many, many common systematic shuffles that are used today are indeed Bessey shuffles, which means they preserve or invert Bessey sequences. And this is now a Bessey sequence relative to the two sets of cards that are of interest to us here. So now you can go ahead and perform a 50% coding. 1, 2, 3, 4. Drop the rest on top. You can do another one of those if you like. You can do the Charlier 1, top to bottom, bottom to top. Now I do have a separate video on the Charlier shuffle that you may want to look at on YouTube on the Hidden Structures channel. So if I went through that too fast earlier, we can do a Bessey 2-2 next. See, this is where you go 1, 2 from the top, 1, 2 from the bottom without dropping them. Sorry. 1, 2 from the top, and 1, 2 from the bottom. And then we can do a Bessey 1-1. So this is just 1 from the top, 1 from the bottom, top, bottom, top, bottom, top, and then bottom goes on top. And then you could even do, well, you just continue to do this until the spectator says, okay, I'm convinced that no human could know anything really about the ordering of these cards, which is a very reasonable conclusion to draw. Now, in some ways, we don't know everything about these cards. Okay? Now, if I were to peek at the bottom, and I know that this is a member of one of those sets, I know which set it's a member of, then I can actually deduce the nature of the top card, the next two cards, and then the fourth card, and then the nature of the fifth, and then sixth and seventh card, and the bottom card I already spotted. Okay? So there's many things you can conclude from this by just knowing the identity of the bottom, but we don't even need to know anything about the exact ordering of these cards because the Bessey sequence structure has been preserved or inverted. And in either case, we can accomplish what we're going to now accomplish. Okay? So the way that I did it, if you remember, how I finished it was I actually did the triangle deal. Okay? And what that does is it undoes a Bessey sequence back to this two blocks of four cards, one on top, one on bottom, and those two sets of four cards are the ones of interest to us. Okay? That's one way to do it. Another way to do it is to just have in your mind's eye, so let me just put these out, sorry, just have in your mind's eye this sequence, 1, 0, 0, 1, 0, 1, 1, 0, okay? And so we're associating the top card with a 1, the next two cards are zeros, the fourth card is a 1, and so forth. So we want to separate the zeros from the 1s. Well, we have a 1 here, so you can go like 1, 0, 0, 1, 0, 1, 1, 0. You've just now separated the zeros from the 1s. We've regained the original two sets of cards that have the special property that we wanted, namely the sum of one set of card values will be equal to the product of the other card values. And that is indeed the case here. And then you can bring out your prediction and just absolutely blow away the spectators that somehow you saw that this would happen. And the fact that these card values do weird things like, let's see, the product of those just happens to come out to be 30, which equals the sum of these. How in the world could anyone see that that was going to happen? And really, in normal life, that is impossible. What I have shown you here is indeed impossible, unless you have some sense of the structure of this packet of 8 cards and the effect of these shuffles on that packet, what it does to it and what it doesn't do to it. These shuffles do not fundamentally destroy the organization of these cards that's of value or of importance to us. They truly don't. Okay? And that's true regardless of whether the shuffle preserves the Bessey structure exactly, the form of it, or inverts it. It won't matter. Okay? Because when we're separating the zeros from the 1s, it doesn't matter if this whole pile happened to be down here and this one happened to be up there. This prediction would still be true. The sum of one of the piles, we didn't say which pile, equals the product of the other pile. We didn't say exactly what pile that is either. It's just the other one. Okay? So anyway, that is an application, once again, of Bessey Sequences and Bessey Shuffles that might be fun for you to share with family or friends. But I hope you're getting an idea that there are countless ways to leverage your knowledge of the behavior of Bessey sequences when performing a whole host of common and useful shuffles employed today. So I appreciate you watching, and take a look at the previous videos in this series if you haven't. And if you have, then I encourage you to watch the next video in this series, which will be the 6th video out of 12 dedicated to Bessey Shuffle diagrams. So thank you again for watching.